Welcome to the last topic on electron configurations, topic 5.6, which is working with the noble gas shortcut. So unfortunately, I am making this video from home after my emergency that came up today. So hopefully things kind of work out and there's no interruptions during the video. And so for this particular lesson, you are going to want your periodic table. And then to kind of start, the idea was yesterday in your activity with filling out the periodic table according to the correct electron configuration, hopefully you saw some patterns. And so you guys color coordinated it different ways. So the things I wanted you to pick up on is there's really three big patterns going on here. And so the first thing is the energy levels increase as you go across. So all of these are energy level 1, energy level 2. We have 3 this way, 4, 5, and then we do start to deviate a little bit with this part down here. And then you also should have picked up on, like here, that the exponent is all the same. So these are all to the first power, second power, starting back over first, going all the way to the 10th power, first, all the way through the 6th power. And then the one that the majority of you use as your color coding scheme is using that we have the S block here, we have what's called the P block here, we have the D block here, and the F block. And so you don't need that roadmap to predict a configuration. All you need is a periodic table. So that's the first thing we're going to do before we start on the notes, is do some writing to our actual periodic table. So the first thing we're going to add to it is here on the left, we can number our energy levels. These are also called periods on a periodic table, these horizontal rows. So we have 1, 2, 3, 4, 5, 6, and 7. The other thing that you can go ahead and add in here is there is an exception to the rule, and that's this region here and this region here. And so what we can do is add in, and let's see if this will work, is we can put this as 3, 4, 5, and 6. This D block here lags behind by 1 energy level, and then down here lags behind by 2, and we can add that here in just a moment. The next thing I want to add to our periodic table is our blocks. So if we draw a little bracket here, all of this is the S block. This middle region here is the D block. Over here, with the exception of helium, is the P block. And down here is the F block. And like I just mentioned, the D block lags behind by 1, meaning you take the energy level you're in and subtract 1. That's how you get your energy level. The F block lags behind by 2. So this portion of the periodic table fits in right here, where lanthanum goes right behind barium and actinium goes behind radium. So for example, actinium follows radium, so 7 minus 2 is 5. So this is all the 5th energy level, F block. And so, like I said, that's all you need for writing an electron configuration. So if I told you, let's write the electron configuration of, say, silicon using just our periodic table, what you would do is this is like our start line on our bubble sheet, our roadmap. So you go here to the left, we're in the first row, so that means that's the first energy level. I know that I'm in the S block because I have 2 of them together, so we would start out as 1s2. Continuing on, I move to the second energy level. This is the S block, and I'm holding 2 there, so we get 2s2. Going across here, we're still in the second energy level. We're in the P block, and we are going to use all 6 of these, so we get 2p6. So here, we're making our way towards silicon again. I'm now in the third energy level, S block 2, so 3s2. Jumping across here, I'm in the third energy level. I'm in the P block, but in this instance, it's not full. We're going to, I said silicon here, so we are 1, 2. So my exponent would be a 2 here, and that's the configuration for silicon. And if you compare that to where I left off, this is where silicon would be at in the 3p 2 spot. So like I said, you don't need that roadmap to write a configuration, and that's going to become important for learning the shortcut, because when you did, I think, fermium the other day with 100 electrons, that becomes very long, and there's a way to shorthand those configurations. So diving in with the notes then, this first part is kind of, again, just connecting and building things we've been doing. So for this first one, we have beryllium, which has 4 electrons. So we know that when we go to draw the Bohr model here, we have 2 electrons on this first ring, and then I'm just going to draw my other electrons in here with my purple marker, or maybe I'll do yellow so it stands out a little bit more. So all 2 the remaining 2 can fit on that outside ring. So from there, we can write our electron configuration like we've been doing. And so beryllium has 4 electrons. So that means when we write its configuration to start, we start here at our first energy level, S block, and it's going to hold all 2. So we start out with 1s2. Then we jump down here to where beryllium is at. We are in the second energy level. This is the S block, and it's the second space over. So it becomes 2s2. So I'm going to go through and fill in the remaining 3 elements, doing the Bohr model and configuration, and then we're going to come back together and work on the new part of it. So the next one we have is fluorine, which has 9 electrons. So 2 on the first ring, and that means all of the remaining electrons are going to go on that outermost ring. And that yellow didn't work the best, so I'm going to put the rest in purple. So now we have our 7 electrons. And so let's write its configuration using just the periodic table. So when I go to do that, I start here at my start line, or hydrogen. So I'm at 1s2. Going to my next energy level, we have 2s2. We jump across, we're still in the second row, but we're now in the P block, and to get to fluorine. So we have 2p1, 2p2, 2p3, 2p4, 2p5. Phosphorus, it has 15 electrons. So going from just the periodic table, again, we have 1s2, 2s2. Going across, we're still in the second energy level, but we're now in the P block, and we're going to use all 6 electrons. Going across into our next energy level, we're in the third energy level now, S block, with all 2. We're getting to phosphorus now, so third energy level, P block, and phosphorus is 1, 2, 3 spots in. So it becomes 3p3. So then the last one here that I have is sodium. Sodium has 11 electrons. So when we look at its placement, again, we know that it's going to start out with that 1s2. We transition to the second energy level here, so we are at 2s2. Followed in our second energy level, P block, 6 spots over, so 2p6. Third energy level, S, and we want to get just to sodium, so 3s to the first power. And then I did forget my electrons here, so I'm going to fill out my Bohr models here. So that gets me to 10 electrons. Okay, so that's everything we've done so far, nothing new. So now I'm going to teach you how to shorthand these and write them in a different format using the noble gases. So that's our next little bit that we're going to cover, is just the families and the general layout of the periodic table. And so Family 18 over here is identified as the noble gases. Certain families have unique names assigned to them. And so the reason why they're called noble gases is they're kind of like nobility in that they are kind of snooty and look down on others. And so these are noble. They look down on the other elements because their electron configurations are full. So that S block is full, that P block is full. And so the noble gases are oftentimes called inert, or they are unreactive. They don't want to form a chemical bond with something. And so we use these as our jumping point because, again, we know the configuration up to that point. And so that, again, is going to use the noble gases, which is all of these here in family 18. So when you go to write a noble gas configuration, what you're going to do is you find the element that you're looking for. So we have beryllium. You follow it across and you move up. You select the noble gas in the row or period above it. So helium is the noble gas above beryllium. So the first thing we're going to do with that is we are going to put helium inside a set of brackets. So then this is why you need to use the periodic table, not your roadmap, because then it's much easier to pick up where you're at. So we've taken care of, by putting helium in brackets, we've taken care of this first part of the configuration. So all we have left to do is write 2s2. And that actually helps show just the valence electrons, because those are the electrons that we really care about. Again, we've established that's on the second ring here, highest energy level of 2. That's the same thing here. This is our highest energy level, 2 electrons. So we have 2 valence electrons, and we have beryllium with 2 dots for its 2 valence electrons. Okay? So fluorine is in the same energy level or same period as beryllium. So same idea, you follow it over, and you are also going to use helium. So everything in this period uses the same noble gas. So fluorine is going to use helium as well. And then you start with your configuration after helium. So you go to your second energy level, S block, 2. So 2s2. Still in that second row, we're now in the P block, and that was 5 spots over. So again, by using helium, it didn't save us much in these 2 examples, but it saved us from having to write the 1s2. So then here, same idea, these are the highest energy levels, and in total with my exponents I have 7 valence electrons, which my Bohr model and my full configuration also shows. So 7 valence electrons for fluorine. So phosphorus moves into a new row. So for phosphorus, I would follow it over, and you move up 1. So the noble gas in the row above it. So neon is the gas that will go in the brackets for this example. Picking up where we left off with neon, we move on to the third energy level, S block 2. Moving over to phosphorus, we are still in the third row, P block, 3 spots over. So 3p3. So the noble gas shortcut helped us get rid of it, summarized all of that part of the configuration by putting it in neon, and this is what's remaining, which that is the configuration for these 5 valence electrons. So phosphorus has 5. So again, you have different means of determining valence electrons for an element. So the last one here is sodium, which is also in the third row like phosphorus. So much like phosphorus, neon is the noble gas in the family above it. So we are going to use neon. And then where we left off, we're in the third energy row, S block with 1. So 3s1. So again, this is summarized here, shows the 1 valence electron in all 3 instances. Okay, so I just have a couple last examples of doing just the noble gas configuration and doing valence electrons from that. So if you take a look, we're not writing the full configuration, we're just doing the noble gas, and we're going to determine valence electrons. So here we have magnesium. So when you find magnesium, you follow it over and move up. So that is the noble gas that will go in the brackets, which again is neon. So that takes you through number 10. So you move on to atomic number 11 for the 11th electron. We are in the third energy row, S block, and magnesium is 2 spots over. So following that, it's going to become 3s2. The third energy level is the highest energy level, and there's 2 electrons stored there. Therefore, we have 2 valence electrons. For titanium, titanium is here in the 4th row. So for titanium, to select its noble gas, we follow over and up. So we select argon for our noble gas. And then we move on from electron 18 to electron 19. We're in the 4th energy level. The S block can hold 2. So 4s2. For titanium, we're no longer in the 4th energy level in this region of the periodic table. This is the D block. You can always remember it because it's 10 elements wide. You subtract 1. So this is where we deviate, and it's no longer, this isn't 4D here, but it is 3D. So 3D, and to get to titanium, we need to move 2 spots over. So this becomes 3D2. And we're not going to do valence electrons. Valence electrons get strange with the D block and the F block. S and P only have predictable valence electrons, and that's actually a topic we'll get into at the beginning of next semester. So we have one last example, and that is bromine. So when you find bromine, it's also in the 4th energy level. So if you find bromine, you move up to argon like titanium. So same pattern, we go to electron 19, so we're in the 4th energy level. S block can hold 2. We deviate to the D block, so we subtract 1, so this becomes 3D. If you count, that's to the 10th power for the 10 electrons. When you go back to P, it follows that pattern with S. So it goes back to the original starting energy level. So this becomes 4P. And to get to bromine, you have 1, 2, 3, 4, 5. So for valence electrons here, you select just your highest energy level, which is the 4. You find the total of your exponents. Therefore, bromine has 7 valence electrons. So that is how you write electron configurations using the noble gas shortcut. If you have any questions, need any help, please reach out to me.